Welcome to Black Hole Basics, where we explore the darkest mysteries of our cosmos, starting with the universe's most violent and bright explosions. Imagine a single explosion releasing more energy in 10 seconds than our Sun will emit during its entire 10 billion year lifetime. These are gamma-ray bursts, or GRBs, the brightest electromagnetic events known to occur in the universe since the massive Big Bang itself. They appear as sudden flashes of gamma rays, the most energetic form of light, appearing randomly in the sky at unexpected times. The story of their discovery is quite fascinating, dating back to the height of the Cold War between global superpowers in the 60s. The United States launched Vela satellites to detect gamma radiation pulses from potential covert nuclear weapon tests conducted by the Soviet Union. Instead of detecting nuclear tests on Earth, these satellites picked up massive bursts of radiation coming from deep space, far beyond our solar system. Astronomers were completely baffled because these mysterious signals did not match any known cosmic phenomenon recorded in human history up to that point. Gamma rays sit at the extreme end of the electromagnetic spectrum, possessing the shortest wavelengths and the highest energy of all light waves. While X-rays can penetrate our skin, gamma rays are powerful enough to pass through thick lead and destroy living cells upon contact. For decades, the origin of these flashes remained a mystery, as they appeared from every direction in the sky, never repeating location. It was not until the launch of advanced space observatories that we began to understand the true terrifying scale of these cosmic events. Scientists eventually categorized these bursts into two distinct classes based on their duration: short gamma-ray bursts and long gamma-ray bursts. Short bursts last less than 2 seconds, yet in that brief moment, they release more energy than our galaxy does in a year. Long bursts sustain their high energy emission for more than 2 seconds, sometimes lasting for several minutes, dominating the surrounding space with light. Long gamma-ray bursts are now linked to the spectacular death of massive stars, specifically those with 20 times the mass of the Sun. When such a massive star runs out of nuclear fuel, its core collapses under its own gravity, forming a black hole or neutron star. This collapse creates a swirling disk of superheated matter falling into the new black hole, generating immense magnetic fields and energy. Instead of just exploding outward, some energy is focused into two narrow jets of plasma moving at nearly the speed of light. These relativistic jets punch through the dying star, and when they breach the surface, they emit the intense flash of gamma rays we observe. This specific type of stellar death is often called a hypernova, a rare and extremely powerful version of a standard supernova explosion. On the other hand, short gamma-ray bursts have a different, equally violent origin story involving the collision of two ultra-dense neutron stars. As these city-sized stellar remnants spiral closer together, they eventually merge, causing an explosion known as a kilonova, releasing a short burst. This merger not only produces gamma rays, but also sends ripples through the fabric of spacetime, known to us as gravitational waves. It is inside these violent kilonova explosions that the universe forges heavy elements, including the gold in your jewelry and uranium for energy. The extreme brightness of a gamma-ray burst is due to a phenomenon called beaming, focusing energy like a laser rather than a light bulb. We can only detect these bursts if the jet is pointed directly at Earth, similar to looking straight into the beam of a lighthouse. If the jet is pointed away from us, we miss the gamma rays entirely and might only see the aftermath as a supernova. Most GRBs we detect occur billions of light years away, meaning we are witnessing events that happened when the universe was very young. In the early universe, massive stars poor in heavy elements were more common, creating ideal conditions for these frequent and powerful bursts. But a terrifying question remains for astronomers and humanity alike. What would happen if a gamma-ray burst occurred right here in our galaxy? If a burst occurred within a few thousand light years and was aimed at us, the results would be catastrophic for life on Earth. The intense radiation would instantly destroy the ozone layer, stripping away our protection against the sun's lethal ultraviolet rays for many years. Without the ozone layer, intense UV radiation would scorch the surface, killing plankton in the oceans and destroying crops on the land. The chemical reactions in the atmosphere would create a thick smog of nitrogen dioxide, blocking sunlight and potentially triggering a global ice age. Some scientists believe a gamma-ray burst may have been responsible for the Ordovician mass extinction event over 400 million years ago. That event wiped out nearly 85% of marine species, and the pattern of extinction matches the effects of a gamma-ray strike. Currently, one potential candidate for a future burst is the star system WR104, located about 8,000 light-years from Earth. It appears to be aligned in a way that, if it were to explode, the jet could potentially be aimed in our direction. However, at 8,000 light-years, the atmosphere might absorb enough energy to save us from total extinction, though damage would be significant. Fortunately, gamma-ray bursts are extremely rare in galaxies like ours, occurring perhaps only once every few million years per galaxy. Our galaxy is rich in heavy metals, which actually make stars less likely to generate the specific conditions needed for a gamma-ray burst. To study these fleeting events, NASA launched the SWIFT satellite, designed to detect a burst and rotate its telescopes in under a minute. SWIFT acts as an early warning system, sending coordinates to ground-based telescopes so they can observe the afterglow before it fades away. The afterglow spans the electromagnetic spectrum, from X-rays to radio waves, providing crucial data about the explosion's environment and debris. In 2008, a burst named GRB 80319b was so bright it could be seen with the naked eye. This was incredible because the explosion took place 7.5 billion light-years away, halfway across the observable universe. More recently, in 2022, astronomers detected the BOAT, or the brightest of all time, a burst that saturated our detectors. This record-breaking event challenged our understanding of how much energy a collapsing star can actually release into the surrounding cosmos. Inside these jets, particles are accelerated to 99.9% the speed of light, riding shockwaves of magnetic turbulence. Along with light, these bursts emit neutrinos, ghostly particles that travel through the universe almost entirely unimpeded by matter. Observatories buried deep in the Antarctic ice search for these neutrinos to help us understand the internal mechanics of the explosion. Gamma-ray bursts may play a crucial role in galaxy evolution, heating interstellar gas and potentially regulating the formation of new stars. They also act as cosmic beacons, backlighting the faint gas and dust of the early universe, allowing us to study composition. Because they are so bright, GRBs allow us to measure the expansion of the universe at distances where supernovae are too faint. Some scientists propose that highly magnetized neutron stars, called magnetars, could be the central engines for certain types of long bursts. The debate between black hole and magnetar models drives current research, as each predicts slightly different signatures in the afterglow data. Supercomputer simulations are now sophisticated enough to model the second-by-second collapse of a star and the launch of the jets. These models show that the jets are not perfectly smooth. They are turbulent and chaotic, which explains the flickering light curves. The James Webb Space Telescope is now joining the hunt, looking at the infrared afterglows to identify the host galaxies of bursts. By studying the host galaxy, we can learn about the environment that gave birth to the star, such as its chemical makeup. There is also a class of dark bursts where the optical afterglow is hidden behind thick clouds of cosmic dust and gas. Recent discoveries have detected photons with energies in the tera-electronvolt range, challenging our theories on how particles are accelerated so efficiently. Ground-based Cherenkov telescopes are essential for catching these ultra-high energy photons that space telescopes are too small to effectively capture. As the jet struggles to punch through the star, it creates a hot cocoon of gas that may emit its own radiation. This cocoon emission spreads wider than the jet, potentially allowing us to see off-axis events that are not pointing directly at us. The frequency of these bursts suggests that life might be difficult to sustain in the dense, star-packed centers of active galaxies. We are lucky to live in the quiet suburbs of the Milky Way, far from the crowded core where bursts are likely. However, some argue that by sterilizing regions of space, GRBs might reset the evolutionary clock, allowing new and different life forms to emerge. Gamma-ray bursts are a leading candidate for the great filter solution to the Fermi paradox, explaining why we haven't met aliens. They serve as a stark reminder that the universe is not a static, peaceful void, but a dynamic and often violent arena. Understanding GRBs requires mastering the physics of extreme magnetic fields, which act as the cosmic gun barrel for these energy bullets. The leading theory for the prompt flash is the internal shock model, where fast-moving shells of matter catch up to slower ones. The afterglow, conversely, is caused by external shocks as the jet slams into the surrounding gas and dust of the interstellar medium. Measuring the polarization of the light helps astronomers determine the structure and organization of the magnetic fields driving the explosion. We have entered the era of multi-messenger astronomy, where we observe the universe using light, particles, and gravity waves all at once. The historic event in 2017 confirmed that neutron star mergers are indeed the source of short gamma-ray bursts and gravitational waves. Future missions aim to launch networks of smaller satellites to provide complete coverage of the sky, ensuring we never miss a burst. Artificial intelligence is also being trained to sift through massive amounts of data to find fainter or unusual bursts automatically. Despite our progress, many questions remain, such as exactly how the central engine converts matter into energy with such terrifying efficiency. Could some gamma-ray bursts be signatures of exotic physics, such as the evaporation of primordial black holes formed in the Big Bang? Studying these cosmic accelerators helps physicists understand matter under conditions that are impossible to replicate in laboratories here on Earth. There is a strange beauty in the destruction, a reminder of the immense forces that govern the life cycle of our universe. The death of a star in a gamma-ray burst spreads heavy elements across the galaxy, becoming the seeds for future solar systems. In a very literal sense, the violent events of the past helped create the atoms that make up our bodies today. Gamma-ray bursts remain the undisputed kings of cosmic explosions, pushing the laws of physics to their absolute breaking point in space. They humble us, showing how small and fragile our existence is compared to the titanic energies unleashed in the dark void. As our technology improves, we hope to not only observe them better, but perhaps one day predict them with greater accuracy. The next generation of astronomers will likely uncover secrets about these bursts that we cannot even begin to imagine right now. Understanding the distribution of radiation bursts is also critical for the safety of future human interstellar travel and deep space colonization. Astronauts on a journey to Mars or beyond would need advanced warning systems to seek shelter from sudden gamma-ray storms. Tree rings have revealed evidence of massive radiation spikes in Earth's past, known as Miyake events, possibly linked to cosmic bursts. A direct hit today would not only damage the ozone, but could devastate our global power grids and satellite communication networks. Yet, our planet has survived for 4.5 billion years, weathering the cosmic storm through luck and resilience. Every time we think we have solved the puzzle of gamma-ray bursts, the universe throws us a new, unexpected surprise. Even amateur astronomers contribute to this field, monitoring the optical afterglows of bursts once they have been pinpointed by satellites. The study of these massive events is a truly global effort, uniting scientists from every continent in a shared quest for knowledge. We have come a long way from the accidental discovery by Cold War spy satellites to the precise multi-messenger observations of today. Gamma-ray bursts serve as the ultimate physics laboratory, testing theories of relativity, gravity, and particle physics in ways we never could on Earth. So the next time you look up at the night sky, remember the invisible fireworks that are constantly lighting up the deep universe. While the stars may seem static and peaceful to our eyes, the cosmos is alive with energy, transformation, and spectacular power. From the collapse of massive hypernovas to the violent merger of dense neutron stars, gamma-ray bursts tell the story of stellar death. They remind us that destruction and creation are two sides of the same cosmic coin, driving the evolution of the universe forever. Here at Black Hole Basics, we are dedicated to bringing you the most fascinating and accurate stories from the frontiers of astrophysics. If you enjoyed this deep dive into the universe's brightest flashes, please consider liking this video and subscribing to our channel. Let us know in the comments below what other cosmic mysteries or extreme phenomena you would like us to cover in future videos. Sharing this video with fellow space enthusiasts helps us grow and allows us to continue producing high-quality content for you all. Creating these visual journeys takes a lot of research and passion, and we appreciate every single one of our curious viewers. You have been watching Black Hole Basics, your guide to the gravity-defying, mind-bending, and awe-inspiring structures of our incredible universe. As the afterglow of our journey fades, remember that there is always more to discover in the darkness waiting to be found. Thank you for joining us on this voyage through the high-energy universe, and for supporting our mission to educate and inspire. Until next time, keep your eyes on the stars, stay curious, and never stop wondering about the secrets of the cosmos. This is Black Hole Basics, signing off. See you in the next video.